Download this code from codegive.com, link in the description below. OK, let's dive deep into real-time rendering software and explore some options with a focus on practical examples. This is a vast topic, so we'll focus on core concepts and a specific example, using opengl with C++. Introduction to real-time rendering. Real-time rendering is the process of generating images, typically animated, at a rate fast enough for a user to interact with them without significant delay. This is crucial for applications like video games, the prime example, where low latency is essential for gameplay. Virtual reality, VR/augmented reality, AR. Motion sickness is a real issue with VR, so high frame rates are paramount. Interactive 3D modeling, architectural visualizations, CAD software, and 3D sculpting tools need to update the view in response to user input. Real-time data visualization, displaying sensor data, simulations, or complex data sets interactively. Key concepts: frame rate, the number of frames rendered per second, FPS. Higher FPS generally means a smoother experience. Target FPS typically range from 30, minimum, to 60, standard, to 90 plus, VR. Rendering pipeline, the sequence of steps involved in creating an image from 3D data. A simplified pipeline includes vertex processing, transforms vertex coordinates, calculates normals, etc. Rasterization, determines which pixels are covered by triangles. Fragment processing, determines the color of each pixel. Shaders, small programs, written in languages like GLSL or HLSL, that run on the GPU and control vertex processing and fragment processing. They are highly customizable. Textures, images applied to surfaces to add detail. Lighting, simulating how light interacts with objects in the scene. Shadows, creating the illusion of shadows cast by objects. Performance optimization, techniques to improve rendering speed, example level of detail, occlusion culling, instancing. 2. Real-time rendering software options. There are several categories of software used for real-time rendering. 1. Game engines. Unreal Engine, Epic Games, a powerful and versatile engine. Uses C++ for core logic and a visual scripting language, Blueprints, for gameplay. Known for its high-fidelity rendering capabilities. Pros. Excellent visual quality, a huge asset store, Blueprints for rapid prototyping, strong community support. Cons. Can be complex to learn, large engine size, license considerations, depending on usage. Unity Technologies, another popular engine, especially good for mobile and indie games. Uses C for scripting. Pros. Easy to learn, cross-platform support, large asset store, good documentation, large community. Cons. Visual quality might not match Unreal Engine out of the box, can require more optimization. Godot engine. An open source, MIT licensed engine that is rapidly gaining popularity. Uses its own scripting language, GDScript, which is Python-like. Pros. Free and open source, lightweight, easy to learn, scene-centric design. Cons. Smaller community compared to Unreal and Unity, fewer pre-built assets. 2. Rendering APIs, low level. OpenGL, Chronos Group, a cross-platform API for rendering 2D and 3D graphics. Requires you to write more code yourself, but gives you fine-grained control. *DirectX, Microsoft a set of APIs for Windows platforms, including rendering, Direct 3D. Similar to OpenGL in terms of control. *Fuken, Chronos Group a newer API designed for high performance and low overhead. More complex than OpenGL, but offers significant potential for optimization. *Metal, Apple's low-level graphics API for iOS and Mac OS. Using these APIs directly means you have to handle the rendering pipeline yourself. This provides maximum control but also requires more effort. 3 Ray Tracing Engines NVIDIA RTX allows for real-time ray tracing using dedicated hardware. AMD Fidelity FX a suite of effects, some of which are ray tracing based, for AMD GPUs. Embry, Intel a collection of high-performance ray tracing kernels. 4 Specialized rendering software Blender This free and open source 3D creation suite can be used for real-time rendering. It features a powerful real-time rendering engine called Eevee. Marmoset Toolbag a popular real-time rendering and baking tool for artists. Substance Painter a texturing tool that also offers real-time rendering capabilities. 3. Choosing the right software. The best choice depends on your project's requirements. For games Unreal Engine and Unity are excellent starting points. Consider Godot Engine for smaller projects. For scientific visualization / custom rendering OpenGL, DirectX, or Fuken might be more appropriate for maximum control. For product demo / architectural visualization game engines or specialized real-time rendering software are good options. For high-fidelity rendering, if hardware allows Unreal Engine with ray tracing features enabled or a dedicated ray tracing engine, if you need maximum performance. 4. OpenGL example, C++. Let's create a simple example using OpenGL and C++ to render a triangle. This example will use glfw, a library for creating windows and handling input, and glad, a library that manages OpenGL function pointers. 1. Project setup, assumptions. You have a C++ compiler, example G++, Visual Studio. You have glfw and glad installed. Installation methods vary depending on your OS. For example, on Ubuntu, you might do sudo apt-get install libglf3dev. For Visual Studio, you'll need to download the libraries and configure the projects, include directories and linker settings. Use a package manager like vcpkg or Conan to simplify dependency management. You understand basic C++. 2. Code, main.cpp. 3. Explanation include necessary headers for OpenGL, glfw, and standard I/O. glfw initialization initializes glfw, sets OpenGL version hints, 3.3 core profile is common, and creates a window. The glfw window hint calls are crucial to tell OpenGL which features and version to use. The OpenGL_forward_compat flag might be necessary for Mac OS. *glad initialization *glad loads OpenGL function pointers. Crucially, it needs to be initialized after the glfw window is created, because it needs an OpenGL context. *vertex shader the vertex shader transforms the vertex positions. In this simple example, it just passes them through. It's written in GLSL, OpenGL shading language. Asterisk fragment shader asterisk the fragment shader determines the color of each pixel. Here, it outputs an orange color. Also written in GLSL. Asterisk shader compilation asterisk the code compiles the vertex and fragment shaders. Error checking is important to catch issues during compilation. Asterisk shader program asterisk a shader program combines the vertex and fragment shaders. The code links the shaders into a program. Asterisk vertex data asterisk defines the vertices of the triangle. Asterisk vertex buffer object, VBO a buffer on the GPU that stores vertex data. Asterisk vertex array object, VAO a container that holds the state of vertex attribute bindings. It stores how the vertex data is laid out in the VBO. Asterisk GL vertex attrib pointer asterisk specifies how OpenGL should interpret the vertex data in the VBO. In this case, it tells OpenGL that the VBO contains 3D floating point coordinates. Asterisk render loop asterisk the main loop that continuously renders frames. Asterisk GL clear color sets the background color. Asterisk GL clear clears the color buffer. Asterisk GL use program activates the shader program. Asterisk GL bind vertex array binds the VAO to be used. Asterisk GL draw arrays draws the triangle. Asterisk GL FW swap buffers swaps the front and back buffers, to prevent tearing. Asterisk GL FW poll events processes events, like keyboard input. Asterisk cleanup asterisk deallocates OpenGL resources and terminates GLFW. 4. Compilation asterisk asterisk. You will need to link against the GLFW and OpenGL libraries. The exact commands vary depending on your operating system and compiler. Asterisk G++, Linux/Mac OS. Asterisk Visual Studio asterisk. 1. Create a new C++ project, example empty project. 2. Add main.cpp to the project. 3. Go to project-properties. 4. C/C++-general-additional include directories asterisk add the path to your GLFW and GLAD header files, example C/glfw/include, C/glad/include. 5. Linker-general-additional library directories asterisk add the path to your GLFW library files, example C/glfw/lib. 6. Linker-input-additional dependencies asterisk add glfw3.lib, opengl32.lib, glu32.lib, and potentially other OpenGL-related libraries. 5. Running the code asterisk asterisk. After successful compilation, run the executable. You should see a window with an orange triangle on a dark green background. V. Advanced real-time rendering techniques, brief overview. This is where the real power and complexity come in. Here are some techniques to consider. Asterisk lighting and shading asterisk. Asterisk Phong shading asterisk a classic lighting model that calculates specular highlights. Asterisk blend Phong shading asterisk a more efficient variation of Phong. Asterisk physically based rendering, PBR a more realistic lighting model based on physical principles, example microfacet theory. Requires textures for albedo, base color, roughness, metallic, normal maps, etc. Asterisk shadow mapping asterisk a technique for creating shadows by rendering the scene from the light's perspective. Asterisk shadow volumes asterisk a more accurate but more complex shadow technique. Asterisk texturing asterisk. Asterisk texture mapping asterisk applying images to surfaces. Asterisk normal mapping asterisk adding surface detail without increasing the polygon count. Asterisk displacement mapping asterisk actually deforming the surface based on a texture. Mip mapping creating pre-filtered versions of textures for different distances. Geometry management level of detail, LOD using lower polygon models for objects that are far away. Occlusion culling not rendering objects that are hidden behind other objects. Instancing rendering multiple copies of the same object efficiently. Post-processing effects bloom creating a glowing effect. Ambient occlusion simulating soft shadows in crevices. Motion blur simulating the effect of motion. Depth of field blurring objects that are out of focus. Color grading adjusting the overall color of the image. Ray tracing, if hardware supported. Ray traced reflections creating realistic reflections. Ray traced shadows generating accurate shadows. Global illumination simulating how light bounces around the scene. 6. Optimization strategies. Real-time rendering relies heavily on optimization to maintain high frame rates. Here are some key strategies. Reduce polygon count. Use LOD techniques or optimize your models in a 3D modeling program. Optimize shaders. Keep shaders as simple as possible. Minimize calculations per fragment. Batch rendering. Draw multiple objects with the same material in a single draw call. Avoid overdraw. Reduce the number of times pixels are drawn on top of each other. Use texturing wisely. Optimize texture sizes. Use compressed textures, example DXT, etc. Profile your code. Use profiling tools to identify bottlenecks. GPU instancing. Render multiple instances of the same mesh with different transformations efficiently. Occlusion culling. Avoid rendering objects that are not visible to the camera. Use the right data structures. Using appropriate data structures for your scene can significantly improve performance. For example, using a KD tree for collision detection or ray tracing. 7. Further learning resources. OpenGL tutorials. Learn OpenGL, https://learnopengl.com. An excellent and comprehensive tutorial for modern OpenGL. OpenGL-tutorial.org, http://www.opengl-tutorial.org. Another good resource. Game engine documentation. Unreal Engine documentation, https://docs.unrealengine.com/n-us. Unity documentation, https://docs.unity3d.com/manual/index.html. Go.engine documentation, https://docs.go.engine.org/n/stable. Books. Real-time rendering by Tomasz Mahler, Eric Haynes, and Nady Hoffman, the definitive reference on real-time rendering techniques. Physically based rendering, from theory to implementation by Matt Farr, Wenzel Jacob, and Greg Humphreys, a deep dive into PBR. 8. Conclusion. Real-time rendering is a complex and constantly evolving field. This tutorial has provided a broad overview of the available software options, core concepts, and a simple OpenGL example to get you started. Remember to practice, experiment, and consult the resources mentioned above to deepen your understanding and create compelling real-time graphics. Choose the tool that suits your goals and learning style. Good luck.